Hi everyone, I'm Adi Gangidi from Meta. Along with my colleagues, I'm here to talk about Meta's large-scale RDMA deployment over Ethernet for AI training. This talk has three parts: introduction and background on AI training workloads, details on the RDMA infra we built in order to support these workloads. Then we can conclude by highlighting some of the takeaways from our work and future considerations. 5 years back, we changed the way we did AI training at Meta. We moved to a GPU full sync training approach that require GPUs to synchronize with each other and their state every training iteration. Along with this change, the model and the data complexity increased manifold. These models required, therefore, different model and data parallel approaches to distribute the work across GPUs. And these parallelisms produced collective traffic patterns. Collective patterns require high bandwidth and low unpredictable latency in order to finish on time, especially to unblock the next GPU computation. In order to satisfy these needs, we followed the following three-part design principle. The first was to develop a deep understanding of the AI training workload. Second was to translate these insights and learnings into designing various aspects of the network. Third was to always operate with a North Star to balance achieving roofline performance while not compromising operational simplicity. So, what did we learn about AI training workloads that shaped our deployment? First, about scale. That scale of the ranking jobs versus GenAI jobs is different. Ranking job scales up to hundreds of GPUs per job, and GenAI job tens of thousands. Scale of endpoints per collective is in hundreds of GPUs per collective in both cases. This is because large GenAI jobs, however large, use 3D parallelism to ensure the number of GPUs per collective operation is reduced to the order of hundreds. Second thing we learned was about parallelisms, that ranking models and GenAI models can use different model and data parallel schemes, and hence can produce different collectives. Further, we observed and learned that ranking jobs produce full mesh traffic patterns for their critical part of communication, which means that they need full bisection network compared to GenAI jobs that produce hierarchical traffic patterns, which means they can run on an oversubscribed network. So what decides whether a job produces a full mesh traffic pattern or hierarchical traffic pattern? It depends on the collectives produced by the job and how these collectives are implemented. As an example of collective algorithmic implementation deciding the traffic pattern, let us look at the all-gather collective implementation. It can be implemented as ring, recursive implementation, or all-to-all. Flow entropy, network congestion, network node topology needed to scale, and the sensitivity to latency, all of these factors vary for each of the algorithmic choice of implementation. If we go by the worst case impact of all of these algorithms, we need to build a network with high injection bandwidth and full bisection bandwidth. This network also needs to offer low baseline latency and route low entropy traffic patterns, as well as deal with any congestion. To solve these requirements from AI training stack perspective to support the growing demand, we designed and deployed a dedicated GPU network capable of supporting RDMA or converged Ethernet. This checked off the high bandwidth, low latency requirement. This also brought a lot of new challenges. Building on top of commodity Ethernet switches helped us better be prepared to solve these challenges, especially because of our prior experience with Ethernet. This also helped us enjoy the vendor diversity in our deployments. Over 5 years of deployments and 3 generations of network endpoint deployments, we documented the highlights of our journey and are about to take you through the same. Here's highlights of our design. We built a dedicated backend network isolated from the front-end network. This backend network uses star-based class topology with deep buffer hieratic switches connecting the racks. For routing, we started with static routing, as it's not sensitive to flow entropy and can deal with low flow entropy collectives as well. But we quickly pivoted away because of some issues found in production to two different approaches in different scenarios. These approaches are traffic engineering and ECMP based on hashing of queue pair ID. We built both of these solutions so that they can support both high entropy and low entropy from a flow perspective in terms of various collectives. For congestion control, we initially started with DCQCN for 200 gig network, but we quickly pivoted away from DCQCN towards using collective communication library mechanism to limit the congestion. To resolve the poor out-of-box performance with Rocky in-house networks, we invested in co-tuning of network as well as collective communication library, successfully bringing our Rocky deployments to roofline performance. We also invested extensively in monitoring of the Rocky stack, learned from production issues so that we can scale operationally as well. So let's dig into the topology. We built separate front-end and back-end networks. This is because the GPU to GPU synchronization traffic demand is going up much faster than the demand for ingestion into the job, ingestion of data to train on the job. In the picture on the right-hand side, we also highlight the topology of the Grand Teton Compute server. Each of our endpoint servers have 8 GPUs and 8 NICs. Our NIC speeds match the GPU PCI speed to ensure maximum possible scale-out bandwidth. And GPUs communicate with each other via high-speed shared memory fabric, like NVLink, and across the servers via RDMA. As it comes to in-depth look at our topology, there are three hierarchical groupings of GPUs, such as racks, AI zones, and DC scale clusters, formed with RTSW, CTSW, and ATSW layers of switching. A rack is formed by 16 GPUs spread between two servers, connected by the RTSW network switch, which is a shallow buffer switch, and is a top-of-the-rack switch. As it comes to AI zone, there are 4K GPUs in an AI zone, and an AI zone is formed by 18 cluster switches connecting many rack switches. This layer of CTSW, which offers full bisection bandwidth, supports ranking jobs as they have a full mesh or an all-to-all traffic component to them, which requires full bisection bandwidth. As it comes to DC scale, a DC scale cluster is formed by connecting 8 AI zones with a new layer of switching called ATSW, and it can fit up to 32K GPUs. This network layer introduces an oversubscription, unlike within the AI zone, because GenAI models running at this scale have hierarchical collective implementations that can tolerate oversubscription. This topology supports extensibility for the future, as we can further extend this topology to larger scale with additional fourth layer of switching or mesh connectivity between various ATSW pods or switches. The usage of the top-of-the-rack topology has immensely helped us, as it helped us use DACs as the first layer of connectivity between within the NICs and the RTSW instead of optics. As we all know, DACs are much more reliable and have order of magnitude lower failure rate compared to optics. Let's dive into a couple of our load balancing implementations. We started with static routing scheme that would map Tor downlink traffic to uplinks based on destination IP prefix. So how does it fare at scale? We noticed that this works well when the destination prefixes are evenly distributed in the job. But in the corner cases where the destination servers are not evenly distributed across all IP prefixes, this would result in 16 downlinks worth of traffic, mapping just to 8 uplinks. To immediately mitigate this, we doubled the uplink speeds, creating undersubscription of 2:1. We were able to get the performance back, but this was an inefficient solution requiring 2x network capacity and hence not ideal. We then tried to implement series of alternate load balancing algorithms that could solve the problem without any extra network capacity. We tried two approaches: a software-based controller to program routes based on scheduling signals. We began with first hop traffic engineering due to the nature of two-stage flow in the AI zone where all the ranking jobs ran. A traffic engineering solution will scale for AI training because it's a repetitive process, producing similar group of traffic patterns, iteration over iteration. So you don't need to update the route program every few minutes. You can program it once and it will last for the duration of your job or whenever a network event happens, whichever happens first. The second approach is to scale ECMP by realizing more flow entropy with existing workloads by doing flow multiplexing. This solution involves two parts: QPair multiplexing of hierarchical traffic patterns by using the collective library, and generating better flow hashing by hashing on the QPair ID field that is part of the Rocky V2 IB payload. We deployed traffic engineering within AI zones meant for ranking jobs due to its performance benefits it saw with all-to-all collectives. But trying to scale it beyond two network hops was a very hard endeavor, and it's operationally complex as it had many, many software parts that were moving. ECMP being operationally simple and having produced near optimal solution or near optimal performance for all other collectives except for all-to-all was deployed for DC scale deployments, where GenAI jobs dominate. In the transport section, we look at momentary congestion. Although routing enhancements took care of persistent hash collisions, we still have momentary congestion and buffering that could happen depending upon the collective traffic pattern. We deployed DCQCN to mitigate this in our 200 gig networks, but we quickly noticed that DCQCN for collectives was a very, very hard endeavor to scale. We either were able to reduce the buffers at the cost of performance in corner cases, or produce only marginal performance benefit, not noticeable much at all, but at the cost of seeing very large buffer watermark buildup. We believe the limited effectiveness of DCQCN is due to the fact that collective library itself has a control loop that limits the amount of traffic posted on the network, which meant that there are two control loops, both operating from sender's perspective without accounting for each other. On top of this, when upgrading to 400 gig networks, we found bugs in the vendor's DCQCN implementation. So for our 400 gig networks, we went without DCQCN, just PFC, and we have been operating these networks for the past 18 months. In the absence of DCQCN, we pivoted to depending on collective library to limit the amount of data posted on the network and hence reducing congestion and PFC. With a single control loop, our visibility of the system and the behavior of the system became more predictable. Looking deeper into how receiver-based control, congestion control, with the help of collective library works, we need to understand the fundamental handshakes involved in collective library in order to understand this in greater detail. Collective library used in Meta over the past few years uses two-stage copy and two-sided communication architecture. This means that the interim GPU HBM buffers are used to buffer the transfer from sender GPU to receiver GPU. Instead of directly writing from the source compute buffer, to the destination compute buffer. Let us call these interim buffers channel buffers. The size of the channel buffer determines the amount of traffic that can be in the flight on the network. Too small a channel buffer, and hence smaller size of transfers on the network, will underutilize the network. Too large a channel buffer will put too much outstanding data on the network and hence would cause momentary congestion. By carefully tuning the size of the buffer and the size of the data transfers, we can control the amount of congestion. Because of the two-sided architecture in the comms library, every transfer is initiated by the receiver with a small clear to send message only when it's ready to receive the transfer, which is after it has finished the previous transaction. Hence, a congested network slowing down the receiver completions will ultimately slow down the rate of the traffic being pumped on the network as well, especially by the sender due to the slow CTS feedback. So in summary, Meta built a large multi-vendor RDMA deployment that supports hundreds of thousands of GPUs with Rocky or 3 generations of GPUs and network speeds. Our experience shows a multi-layer flow topology can scale reliably for AI training workloads. We propose and showcase novel routing solutions such as enhanced CCNP and traffic engineering and showcase that they are optimal for different AI workloads. We showcase the corrective library and the statically carved buffers that they help deal with momentary congestion, complementary to DCQCN. Finally, we showcase that the roofline collective performance can be achieved for our Rocky clusters with the help of collective and network core tuning. In terms of future questions to be answered that we would like to help to see from the larger research community, the first question is whether it's possible to achieve roofline completion time and reliable network and communications experience by building a topology with shallow buffer switches. Meta built most of our deployments with deep buffer switches, but we understand shallow buffers are more efficient. But at the same time, this topic requires more careful understanding because it could be a trade-off. Apart from this, there are multiple other research questions around coming up with a generalized routing solution that works for all AI traffic patterns, or how to deal with increasing round trip time or latency in AI training clusters in order to support larger scales, or fungibility of the networks we build in order to support various AI training workloads. Thank you so much for listening.